So I wanted to briefly mention one last example, which you've actually got in the reading from ModSim, which is also a problem that I'm asking you to do on the packet, but I thought it was worth just highlighting one of the key ideas on it. It is the skateboard problem, which you know and love from last semester, and which you'll come to know and love even more this semester since I'm actually asking you to do it for real. The comment I wanted to make on this is simply around having multiple objects involved when you're doing rotation and translation. So in this particular problem, it's actually set up in a way where you only have to deal with translation for one object and only have to deal with rotation for the other object. So we've got this ramp, which we'll say is length 2 times big L, mass big M, and we've got this block, which we'll say is mass little m. And the sort of problem here is that the ramp is free to rotate, and the block is free to slide up and down the ramp, and so we need to figure out how can we model this motion. Well, in order to model the motion, as always, we need to figure out a coordinate system. I think a clear choice of coordinate system here is a polar coordinate system. So you choose this as theta and this distance as r, and so the position of the block would simply be r times r hat, and the position of the ramp is simply going to be given to you by theta hat. If I then think about abstracting this to free body diagrams, I'm going to cut this block out and think about what the forces are that are acting on the block. Since the block I'm just treating as a particle, I can simply think about forces on the block. And so I cut the block out of the rest of the universe. One force that's going to be acting on it is gravity, and the other force that's going to be acting on it is a normal force from the ramp. And note that that normal force from the ramp is a constraint force. It will be whatever it has to be. It is not simply the component of the gravity that points normal to the ramp. Okay? By the same token, if I think about the ramp, right, since the ramp is purely rotating, the only thing I really need to think about from a free body diagram perspective are the forces that are acting that give us a torque. Right? So it's certainly true that there is gravity acting at the center of the ramp. There's a normal force due to the pin at the center of the ramp. Neither of those matter because they're both acting at the center of the ramp, so they don't actually do anything from a rotational perspective. The only force, so this is N pin, the only force that actually matters is the fact that if the ramp is applying a normal force to the block is applying an equal and opposite normal force to the ramp. Okay? Now once I've done that, then I can start to say, okay, what are the sum of forces on the block? Well, the sum of forces on the block tells me what the mass times the acceleration of the block is, right? Since the block is only a particle, I only need to think about sums of forces on it to figure out equations of motion. By the same token, if I think about the ramp, the only thing I need to think about is sum of torques on the ramp, which tells me the time rate of change of the angular momentum of the ramp, or the moment of inertia of the ramp about the center of mass times theta double dot. So the thing I want to highlight here is just this idea that when you start to deal with rotational and translational motion in multiple bodies, you need to actually abstract the system into subsystems, and you need to think about both what the interactions are that come from the rest of the universe into that subsystem, and also interactions between one part of the one subsystem and the other subsystem. So for example, this normal force is internal to the entire system, but it's an interaction between this subsystem that we're drawing a free body diagram for and this subsystem that you're drawing a free body diagram for. And certainly you can actually do the same thing if you tried to abstract a different system. So say you were talking about a bicycle. If you were to break this bicycle up into parts, you would say, okay, there's a force that's being applied to the rear wheel by this chain, right? Which means in turn that the rear wheel is applying a force to the crank by means of the chain, right? So you do the same thing of breaking up the subsystems, then identifying the internal forces that act between subsystems, as well as the forces, say, between the ground and the bike, or between gravity and the wheels, and gravity and the frame. So again, when you've got some system that has multiple parts, and some parts are rotating, some parts are not rotating, you can use the same kinds of strategies that we have used when dealing with multiple part bodies with particle motion. It's just you now need to start to take torque into account as well.